Hello, this is Calculus 1, Lecture 10b, the mean value theorem and its implications. My name is Scott Grizzard from the University of South Florida. So last time, remember that we talked about proof by contradiction and we did Rolle's theorem. Today, what we want to do is we want to use Rolle's theorem to prove the mean value theorem. So we want to state what the mean value theorem is, that we stated at the end of last lecture. Then we want to prove the mean value theorem using Rolle's theorem. And then we're going to play with using the mean value theorem, and then we're going to prove this thing that derivatives determine the shapes of graphs. In other words, if two functions have the same derivative, then their shapes are identical. They're just vertical shifts of each other. And we need that in order to prove the Fundamental Theorem of Calculus Part 2 at the end of the course. So just recall from last time, we talked about the first of these kind of three. So there's three really big theory lectures. In the first of these, which would have been 9b, we talked about Fermat's stationary point theorem. Then last time we did Rolle's theorem, okay, and we proved it using Fermat's stationary point theorem and the extreme value theorem. Today, what we're going to do is prove the mean value theorem and then this vertical shift, same derivative vertical shift theorem, which is important for us to prove FDC2. So that's where we are. Now, in order to do that, we need a couple more pieces. Now, remember that the linearization had this kind of functional form called, it was the functional form of the tangent line. So I had this idea that the linearization of f based at point A was f of a plus f prime of a times x minus a. And that came from this kind of y minus y naught equals m times x minus x naught, right? That was the equation for a point slope formula. Well, now I'm going to do the exact same thing, except I'm going to do a secant line instead. Okay? So what that's going to look like is something like this, right? Here's my A, here's my B, right? This is A, f of A, there's B. I could just label this A. So there's A, f of A. That's the slope of the secant line. And there is B, f of B. So this right here is the secant line. The red thing is f. This is the line from A, connecting A to B on the graph, okay? So that's the functional form of the secant line, and compare that to the functional form of the tangent line, which is right here. Okay, so that's what that definition says. Now, the reason I'm going to do that, if we look at Rolle's theorem, okay, what I really have here, because f of a had to equal f of b, what I really have here is a secant slope of 0, right? I have a line connecting those two. And then if we look at f prime, what this says is that there exists a u in the middle so that f prime of u equals 0. In other words, f prime of u equals the slope of that secant line. Well, in this context, there's nothing really special about that secant line having a slope of 0. So the mean value theorem is going to say, okay, if I just have a secant line of any type, there's going to be a u in the middle, so that f prime of u is going to, the slope of this tangent line is going to be slope of this tangent line is going to equal the slope of this secant line. In other words, this tangent line is going to be parallel to the secant line. And that's a perfectly good, interpretation of what's going on. So let's look at what we have, again, on this graph. Here is my A, f of A. I've got a slope of 0.25, a B, f of B, right? There's the line I'm talking about. And there's some u in the middle so that the derivative is close. It's not exactly the same. Let's see if I can find the 0.25 that's down here. There's actually two places on this one. Okay, well, that's as close as I'm going to... Right, that's close enough. So I can just keep going, but there is a place here where there is one. I just have to keep, if I have to keep adding decimals until I would find it. Okay, so there we go. Okay, so that seems to have added enough decimals in order to get me in between. So there's the idea. There's some u, there's one up here and there's one down here, but I know there's at least one where f prime of u is going to equal the same as that slope. I've got something parallel. This one was above, this one was below. Okay, well, that's interesting. That's what the mean value says. Okay, there exists some u in the middle so that f prime of u equals mb. So now, how do we prove this? Well, again, this is almost Rolle's theorem. Okay, in fact, it's Rolle's theorem, except that I have this other slope, so, the secant line. So what would happen if instead I subtracted the secant line? Okay, so if I subtracted the secant line, I would wind up with this function down here. That is this function here minus that line. So notice that that pulls this point down to 0, and it pulls this point down to 0 and kind of tilts the graph a little bit. So what I have here is a function that I could apply Rolle's theorem to. So I apply Rolle's theorem to G. I apply Rolle's theorem to G, and then what I do is I get, that flat tangent line there. It's flattish. And it's flat, right? Times 10 to the negative 9, right? There's some rounding error going on decimals. Okay. So what I do is I find that flat, that point, and then what I'm going to do is add back the secant line, and that will give me the u. The same u that works here will also work there, right? This is the exact same x value. Okay, so what I'm going to do, my strategy for this proof is going to be to subtract the secant line. I'm going to form a new function by subtracting the secant line from f. Then I'm going to apply Rolle's theorem to that function. And then what I'm going to do is I'm going to add back the slope of the tangent line, and I'm going to wind up with the u that I'm going to show that I have the u I want. Okay. Let's do that. So, okay. Now, the secant line is a line. Okay? And I've got three things that I have to show here, right? I need to show that that f is continuous, that my new g is continuous on AB, my new g is differentiable on AB, and I need to show that g of A equals g of B. So let's do that. So the first one I need to show is continuity. Well, note here that that thing is a line, right? That equation describes a line. Well, lines are continuous, and they're differentiable everywhere. This is a polynomial, right? I can multiply it out, but it's also just a line. Okay, so I have a function that describes a line. That means it's continuous everywhere, it's differentiable everywhere, and its derivative is simply the slope of the line, right? If all I have is a line, then its derivative is its slope, right? Forget about f and everything associated with it. I'm just looking at this function right here. That function is a line, okay? It's continuous everywhere because it's a line. It's differentiable everywhere because it's a line. And its derivative is its slope everywhere. The slope is constant. Okay, so what that means is that if I have a continuous function minus a continuous function, that's continuous. I have a differentiable function minus a differentiable function, that's differentiable, right? So we need to just write those things out. Okay, so since f is continuous, f minus the secant line is also continuous on AB. Both of these functions are continuous. So the sum law of limits tells me that their limit, that what I'm going to wind up with is also a continuous function, right? The limit from the left, I'm going to just subtract the limits from the left to get the limit from the left. I subtract the limits again to get the limit from the right, and then I subtract the function, and they're all equal, right? The limit from the left equals the limit from the right equals the value of the function. Likewise, since f is differentiable on AB, the f minus s is also differentiable on AB by the sum rule for derivatives. So I've met both condition 1 and condition 2 of Rolle's theorem. The only one left is condition 3. So I have to show, and if we look at our graph again, we'll see what happens here. When I subtract this from this, I'm going to wind up with 0 here and 0 here. Right here at 4, I've got 0. Right here at -1, I wind up with 0 on my new g. So this green line here is my new g. And when I subtract those out, I'm going to wind up with 0. But let's go ahead and do the algebra for that. Okay, so S of A here, remember this is S, F, A, B of A, right? I'm not considered in all the X's, I just want the single X. So G of A equals F of A minus S of A, which is F of A. Now S of A is F of A plus MAB of A times A minus A. Well, this bit is going to be 0. Those two, when they subtract, they're going to come out to be 0. Let me just go ahead and write out what G of A actually, G of X equals here so you can see that better. So there's the equation for my G of X, right? I took F of X and I subtracted here this right here, which was S of X. Well, if I do that, I'm going to wind up with this A minus A being 0. And then that's going to have F of A minus F of A is going to equal 0. So this is me evaluating G of X at A. So G of A equals 0. Now G of B is the other one I need to compute. I need to show that that also equals 0, because what I want is G of A to equal G of B. So this, when I subtract down, I also wind up with 0. Let's see the algebra. Okay, that one's a little bit less clean, right? I've got a B minus A. Well, let's work it out and see what happens. Now, MAB, that, remember, is the slope of the secant line. So that's F of B minus F of A over B minus A. That's kind of nice. I've got B minus A on the bottom and B minus A on the top. Those are going to cancel and go to 1. And notice here I'm distributing another negative. So what I've got now is F of B minus F of A minus, now don't forget to distribute that negative, F of B plus minus F of A. Well, those two cancel, I wind up with 0 again. So now I've got the third condition of Rolle's theorem is met. All right, so all three conditions were met. That means that there exists some u in the middle. So I've got my some u. There's some u, don't know where it is, but there's some u in the middle where g prime of u equals 0. So now I have shown that this point right here exists. Okay? And remember, I'm interested in this point here. So now I've shown that that exists. Now my only problem is I need to add back, right? I need to add back the slope of the secant line, right? I need to add back the secant line to get this function, and then I'll have that slope there is what I want. So let's look at that. So what I'm going to do is basically make an argument about what g prime of u actually equals, or f prime of u. So f of x equals, if g of x equals f of x minus s of x, that means that f of x equals g of x plus s of x. Right? And I already said that this right here was MAB, right? Because this is just a line. Well, then at my u, g prime of u is 0. I just proved that, right? G prime of u equals 0. So that means it goes away, and all I'm left with is the slope. So I added back in the derivative of s, and because the g prime of u is equal to 0, I wind up with a place where f prime of u equals 0, equals MAB. So that's the proof there for the mean value theorem. Okay. Again, the big idea, I subtract the secant line from f, I apply Rolle's theorem, then I add the slope of the secant line back, right? So I add s prime back to when I get f prime. Okay, so let's do an example using how we use the MVT. So suppose that f is differentiable everywhere, and f of 0 equals 5, and f prime of x is less than or equal to -1 for every x. What I want to do is I want to prove that f of 5 is less than or equal to 0. There are a couple ways you can do this. I think the cleanest is just to go, suppose otherwise. So what I'm going to do is I'm going to suppose otherwise, and then I'm going to apply the mean value theorem here. Okay. Well, I said f is differentiable everywhere, and I said that f being differentiable everywhere means that f is continuous everywhere. So the mean value theorem will apply. Okay. So suppose, right, so I supposed my two preconditions here, and I also supposed that my conclusion was false. So f of 5 being less than or equal to 0 means that f of 5 is greater than 0. Is not less than or equal to 0 means that f of 5 is greater than 0. I need an AB. Well, 0 is the smaller one, 5 is the bigger one. Now, I've got an issue here, all right? I'm going to have an inequality. I've said that f of 5 is greater than 0. Now, so what I'm going to do is I'm going to put f of 5 here, right? I'm going to do the slope of the secant line is f of 5 minus f of 0 all over 5 minus 0. Now, here's a little note. If you're dealing with inequalities, you want the thing that you're doing that you've got an inequality for to be in this particular space. And remember that f of b minus f of a over b minus a is the same thing as f of a minus f of b all over a minus b. So the reason why I want to do that is that when I sub in my inequality, I don't have to flip any signs, okay? If the thing I want is here or here, I don't have to flip anything, okay? And I like that, okay? So what I see, let me show you what I mean. So I've got f of u equals this, and then I've got, and that this right here has to be greater than f prime of u has to be less than or equal to -1, okay? So what I'm going to do is I'm going to do this right here. I'm going to say, okay, well, that means that f prime of u, so I've got f of 5 minus f of 0 all over 5 minus 0. And I know that f of 5 is greater than 0. That was my assume otherwise. So I've got on the top, I'm going to have 0 minus 5 all over 5 minus 0. So that's going to be -5 over 5, which equals -1. So f prime of u is greater than -1. But notice that violates this assumption. Right? So now I have my contradiction. And that's how it works. I used it basically exactly like I did the mean value theorem. The only big difference though, is I've got these kind of weird inequalities showing up. And as I said, the trick is to, when you do the inequality, make sure it's right here so you're not messing with, right? I've got f of 5 here and I've got f of 5 here. And by making sure that this was the thing that I was dealing with the greater than sign, it made it so that I didn't have to like flip the inequality because it was multiplying by negative when I was subbing it in, which is just a pain. Okay. So that's how you do one of these kind of example problems with the MVT. And there are similar problems in your book. Okay, so we have the mean value theorem now. Now, the mean value theorem is used to prove a lot. So if we look back up at our list of stuff, the mean value theorem is used to prove like the first derivative test, the second derivative test, the concavity test, increasing, decreasing, all of these things that we have been doing in class with the problem sets. All of those things, you use the mean value theorem to prove them. And if you're looking for those proofs, I'll put some links to the videos below that other people have done, or maybe that I have done. But if you also want to find them, you'll find them in the back of the textbook in one of the appendices. Rolle's theorem is also used to prove something called the extended mean value theorem, which is very similar, except it's got a little bit more oomph, which you use then to prove L'Hopital's rule, the full version. But for us, we want to show that antiderivatives are vertical shifts of each other. Okay. In other words, derivatives determine shape. So if f and g are differentiable on some interval d, okay, and f prime of x equals g prime of x for all the x's, then there's some constant c, so that for every x, f of x equals g of x plus c. In other words, they're vertical shifts of each other. So we've already had the converse of this. We've already know that if two functions differ by a constant, they're going to have, we already know that, they're going to have the same derivative. Right? So we want to prove that this is the only way that that circumstance can happen. Okay, so just to give you an example, if f prime of x equals g prime of x, let's say it equals the derivative equals 2x cubed, then x to the fourth over 2 works. So does x to the fourth over 2 plus 5. So does x to the fourth over 2 minus 5. They differ by a constant. Okay. Now, you may have said, well, wait a minute, what about arc cosine and arc sine? Don't they have very similar derivatives? And the answer is yes. If I have negative arc sine, I'm going to get negative 1 over, right? It's 1 over the square root of 1 minus x squared with a negative in front because of the negative. And if I take arc cosine, I wind up with negative 1 over the square root of 1 minus x squared. So aren't these two functions, negative arc sine and arc cosine, vertical shifts? It turns out they are. If you graph them, you find out that they differ by pi over 2. Okay, so these two shifts, negative arc sine and arc cosine, are simply vertical shifts of each other. Okay, so how do we prove this? Okay, well, we're going to assume otherwise, like we did before. And then what we're going to do is we're going to say, okay, if we assume otherwise, that means that there exists 2 points where they aren't, where they shift with different things. So that f of a minus g of a and f of b minus g of b aren't equal to each other. So if they aren't fixed, if there's not some constant c, that means there are 2 points where they're different. Okay? And then what we're going to show is that if we use the MVT, we're going to find a place, right, where their difference, right, does not equal 0. But it's going to turn out that since f and g are, f prime and g prime are equal, that difference, that derivative has to equal 0. So what we're going to do is we're going to define an h, which is f of x minus g of x, and apply the mean value theorem to that h. Okay. So let's go ahead and do that. So here's our strategy. We're going to, so the proof. Okay. So what I'm saying is suppose otherwise. That means that there's some 2 points, so that f of x plus g of x, I'm sorry, so f of a minus g of a does not equal f of b minus g of b, right? So I'm assuming that the theorem is false. Okay. So that's going to be my strategy. Okay, so that's what I'm going to do here. It's a little proof by contradiction. There are a couple of other ways to do this proof. This is, I think, one of the cleaner ways. You can do it. The book does it constructively without assuming otherwise, but it does it in 2 pieces. So you can, you're welcome to use that version if you prefer it. It does not assume otherwise. I don't think it's quite as clear, but you know, if you think it is, then that's you think it's better. Go ahead and use it. Okay. So that's the idea. I'm assuming otherwise. And if I assume otherwise, then there's, right, this is what it should be. If I assume otherwise, right, all of these things just differ by a constant. But if I assume otherwise, that means that there is an a and a b which doesn't differ by the constant. Okay? And that's what I'm saying. And then I'm going to let h prime of x is going to equal f prime of x minus g prime of x. And that's going to be true because f prime of x equals g prime of x. So I know that that thing's 0. Now, I also know that these 2 things don't differ by a constant. Okay? So that means the following. And that means that h of a does not equal h of b. Right? So I know that this slope, MHAB, the slope of the secant line, does not equal 0 because h of b and h of a are not equal to each other. Okay? So I know that that doesn't equal 0. So those are the parts, right? I'm going to have somewhere in the middle, I'm going to wind up with a place where this has to equal 0, but it can't. Okay, so I'm gonna wind up with somewhere where this slope, right? I know that there has to be a point where the slope equals MHAB, right? The slope of the secant line for h. I usually just say MAB, but here it's not exactly it's not exactly unambiguous. I'm saying the h there. Okay, so I'm gonna get that with the MVT, right? So I know it's differentiable everywhere. F and G are differentiable everywhere. So H is differentiable by the sum rule. H is then just differentiable on the somewhere, AB, and then H is continuous everywhere, therefore continuous on the closed. Okay? And that means I meet the conditions for the mean value theorem. By the mean value theorem, then, there exists a U in AB, that should be the open, so that h prime of u equals 0. Well, I'm sorry, not 0. H prime of u equals m h a b. But MHAB cannot equal 0. Okay? I'm sorry. But h prime of u equals 0 because for f of prime of x equal g prime of x. So I come to a contradiction. And that's the proof. So we're going to use this proof later we proved the Fundamental Theorem of Calculus Part 2. So we need this little tidbit. Okay, to do that. Okay, there's one last thing about the secant line. This is not about MVT. This is just about the secant line. I can actually use the secant line to define concavity for things that aren't necessarily differentiable. Okay, so what I'm going to do is let f be continuous on some interval d. And then I'm going to say that f is concave down if for all ab that's a subset. So for every interval, closed interval that's a subset, a little weird, f of x is greater than the secant line. So basically what I'm saying is that the secants run below. So if the secants run below, I'm concave down. If the secants run above, I'm concave up. Now compare that to what I had before. F is concave kind if the tangent lines run above, but the secant lines run below. So that's all you have to kind of remember about this little theorem. And if we look here, we can actually see that on this on our functions that we were playing with earlier. Okay, so here, of course, it's set up here for this area right here, right? From, let's say this is my interval and this is my interval here. Now here, you'll notice that the tangent lines for this interval run above. Okay, let's give some interval here. Now we'll just let it be this. But here, the secant lines run below. Okay, and that's so basically it. That means that this section of the graph is concave down. Okay, because the secant lines run above, and the secant lines run below, and the tangent lines run above. Okay, and again, as usual, there will be a link for this graph in the description so that you can play with it yourself. Okay, so that's what I have for you today. It's just this, we went over a couple things. We talked about the mean value theorem, and we proved it. And we talked about this functional form of the secant line, and then we used it in the proof for the mean value theorem. Then we proved that if derivatives determine the shape of graph. If f prime equals g prime, then f and g are just vertical shifts of each other. And we also went over, we kind of generalized concavity using the secant line. So something is concave down if the tangent lines run above, or if the secant lines run below. They're the same. One of them's a little bit more general. Okay, well, that's what I have for you, and I will see you next time.